In the summer of 1940, RAF pilots discovered their engine had a fatal flaw that only appeared in the moment they needed it most. Push a Spitfire into a steep dive to chase or escape an enemy fighter, and the engine would stumble, cutting out completely right as full power mattered most. German pilots learned the trick fast: dive away and the British engine behind you falters. This is the story of the engine that carried Britain through its most desperate years of the war. Despite that flaw, and because of the mathematical triumphs that came after it, the engine began life with no government funding at all. In 1933, Rolls-Royce started building a private venture 12-cylinder engine, the PV12, betting the company's own money that a war was coming and Britain would need it. 6 months before the engine first ran, the company's co-founder Henry Royce died. He never saw it fly. The early P12 struggled. It leaked, overheated, and made barely 750 horsepower on the test stand. Rolls-Royce built and scrapped over 30 prototype engines chasing reliability. But by 1936, a reworked 27-liter version was ready, renamed after a bird of prey, the Merlin. 2 new fighter designs were built specifically around it: the Hawker Hurricane and the Supermarine Spitfire. By 1940, the Merlin was producing roughly 1000 horsepower, but it faced a brutal reality. The German Messerschmitt Bf 109s used fuel-injected Daimler-Benz engines. The Merlin relied on a float-type carburetor. When a pilot pushed the stick forward to dive, negative G-forces would throw the fuel in the carburetor bowl the wrong way, starving the engine, then flooding it. The engine choked right when the pilot needed to chase or escape a diving enemy. The fix didn't come until 1941. After the Battle of Britain was already won, an engineer at the Royal Aircraft Establishment named Beatrice Shilling designed a simple restrictor, a small brass fitting with a precisely calculated aperture fitted straight into the fuel line. Later simplified into a flat metal washer for faster production. Either way, it kept fuel flow at exactly what the engine could consume at full throttle, stopping the flooding entirely. Pilots called it Miss Shilling's orifice. A crude patch, but it kept them in the fight. Keeping up wasn't enough, though. As bombers climbed higher, engine power thinned out with the atmosphere. To win, they needed to dominate the stratosphere. Enter Stanley Hooker. He wasn't an engine mechanic. He was a mathematician trained in hydrodynamics and aerodynamics at Oxford. When he looked at the Merlin supercharger, he didn't see metal. He saw airflow. He found the early supercharger's intake path was wildly inefficient, robbing the engine of power in thin air, and applied pure mathematics to smooth the intake curves and optimize the impeller. But his masterstroke was the two-stage, two-speed supercharger. Compressing air naturally heats it up, which reduces its density, the exact opposite of what you want for combustion. Hookers designed compressed air through 2 successive impeller stages, then passed it through a liquid-cooled intercooler before it reached the cylinders, dropping the temperature and packing in denser, oxygen-rich air. The resulting Merlin 61 didn't just maintain power at 30,000 feet, it increased it, giving the Spitfire Mark 9 a real speed advantage at altitude for the first time. Engineering alone wasn't the whole story though. In 1940, the RAF switched from 87 octane fuel to 100 octane fuel, imported in bulk from the US and Caribbean refineries. Higher octane resists engine knock, which let engineers push boost pressure further without the engine tearing itself apart. Early Merlins ran at 9 pounds of boost, with Hooker supercharger and 100 octane fuel that climbed to 18 pounds. By 1944, running on 150 octane fuel, some variants reached 25 pounds of boost. The result, horsepower that had started under 1000 climbed past 2000 in the Merlin 130 and 131. Built for the de Havilland Hornet without changing the engine's original 27-liter displacement. This obsession with optimization reached its peak with a different airframe entirely. The American P-51 Mustang was beautifully aerodynamic, but its Allison engine ran out of breath above 15,000 feet, exactly where bomber formations needed protection most. In April 1942, Rolls-Royce test pilot Ronald Harker flew a Mustang and suggested something simple: drop a Merlin into it. The combination was transformative, built under license by Packard in the United States. The Merlin-powered Mustang gained 50 miles an hour at altitude. For the first time, a single-seat fighter could escort heavy bombers all the way to Berlin and back, fighting at exact altitude the mission demanded. By the end of the war, Rolls-Royce in Derby, Ford in Manchester, and Packard in Detroit had built over 150,000 Merlins between them. The Merlin didn't win the war by being flawless. It won by being fixable. A carburetor patched mid-service, a supercharger redesigned with pure mathematics, and an engine handed to a foreign fighter it was never originally built for. Henry Royce never lived to see it, but the engine that carried his initials outlasted the war it was built for, and outlasted him by decades.